Welcome to this lecture series in group theory. In this lecture, we'll see two applications of the Coset action, and let us recall some relevant things. So first of all, what is the definition of the Coset action? Fix a group G and a subgroup of it, call that subgroup H. Then there is a action of G on the set of all the left cosets of H in G, defined in this way. So it takes, if you hit a coset by a group element G, then if X is a representative of this coset, you get the coset whose representative is Gx, and we saw that this is well defined. All right, and yeah, so this is a transitive action. Perhaps I didn't say that, but it is clear that this is a transitive action. So this is a transitive action, and its kernel we observed is equal to this thing, intersection of all the conjugates of H. We noticed that it is the largest normal subgroup of G which is contained in H. So this is a normal subgroup of G simply because this is the kernel of a group homomorphism, but it is actually the largest normal subgroup of G that is contained in the subgroup H. And we also saw that if H is finite index, then so is, if H has a finite index in G, then same is true for the kernel of the action. And further, we noticed that the index of the kernel divides the factorial of the index of the subgroup H. So these were the three properties that we proved. Also note that this is a general nonsense about group actions. So suppose I have a group acting on a set X, and K is the kernel of the action, then there is a natural action of G mod K on X. I don't know if I established this earlier, but this is very simple. So basically what is going on is suppose we have an action of the group G on some set X. So basically we are given a homomorphism. And if K is the kernel of this group homomorphism, then we get a homomorphism like this, just by the first isomorphism theorem. So we get an action of G mod K on sim X, and if we want to write it in the other perspective, then it's just as this Gk dot X is nothing but Gx. Sorry, G dot X. So that's how, if you just decode from this picture, this will be the definition of this action. So there's a natural action of the quotient group on the set that we were acting on. All right, so let's, so these are three simple problems. We have a new definition before we attempt those problems. That's the definition of a maximal subgroup. And now let us get to the material of this lecture. So here's a lemma that is very, very common, or I don't know, it's very popular in any group theory course. It's a very strange kind of lemma. I find it sort of a peculiar lemma, but it's also very useful. When you want to discuss the nature of some given group, let's say a group of order something, 10, 15, something like that, this is a useful lemma. Okay, so what is a lemma? We have a finite group G, and we have a prime, and suppose P is the smallest prime that divides the cardinality of the group. Amongst all the primes that divide the cardinality of the group, pick the smallest one. Then we show that any subgroup of G whose index is that prime is actually a normal subgroup. Pretty strange statement, and it's not easy. It's a non-trivial proof. And I suppose this is the only proof I know, the proof that I'm going to give. So this is how it goes. We consider we want to show that H is normal. So we can use what we have developed in the previous lecture, or what we just discussed in the recap. So consider the action of G on G mod H. And let's say N is the kernel of the action. So we know we know precisely what it is. Let me write it down, although we won't need it. So this is the kernel of the action. But the important thing is that this is the largest normal subgroup of G which is contained in H. Amongst all the subgroups of G that are contained in H, this is the largest one, meaning it contains every other normal subgroup that is contained in H. So goal is what? Our goal is to show that. Goal is to show that N is equal to H. Right? If we want to show that H is normal, then H would be the largest normal subgroup of G that is contained in H. And hence it is equivalent to showing that H is equal to N. So that is how we are going to go about it. And we now use the other property that the index of the kernel of the homomorphism, or rather kernel of the action, divides the factorial of the index of the group we are, the index of the group whose left cosets we are acting on. So we know this by our previous lecture, which we also discussed in the recap. So what we know is that G mod the index of the kernel divides P factorial, because P is the index of the subgroup H. Okay, so let's say K is some positive integer such that the index of n is equal to times K is equal to P factorial. All right, so far so good. Let us write let us write it this way. We will write the index of n this way, and the right hand side let us write in this way: p minus 1 factorial times p. So we get this upon p times k is equal to the cardinality of n times p minus 1 factorial. Just a manipulation. K is not some subgroup, K is a number. Okay, so note that this is an integer because p divides mod g, that's in the hypothesis. So this is an integer, this is an integer. Of course, these two are integers. So we see that p minus 1 factorial divides the left hand side. But at the same time, this guy, p minus 1 factorial, is relatively prime with mod g because of the hypothesis that p is the smallest prime that divides mod g. And every prime that divides p minus 1 factorial is smaller than p, obviously. Therefore, p minus 1 factorial is relatively prime with mod g, and hence p minus 1 factorial is relatively prime with mod g by p. So I do not want to write all that. Let me just write the conclusion of what I just said is that GCD of p minus 1 factorial with this number is 1. So this we just argued, and hence this implies that p minus 1 factorial divides k. Right? If this guy divides the product of two numbers and this guy is relatively prime to one of them, then it has to divide the second guy. Okay, so what we can do is, so maybe this implication I'll write here. So we have that implication, and therefore we have, yeah, so what is this? This is the cardinality of H, because the index of H is P, therefore mod G by P is cardinality of H. So we get mod H k upon p minus 1 factorial equals mod n, or cardinality of n, which implies that cardinality of n is at least the cardinality of H. Why is that? Because we just argued p minus 1 factorial divides k, and hence this is at least 1. And since this is equal to mod H, it is now clear that the cardinality of n is at least as much as the cardinality of H, but n is contained in H. Combine this with the fact that n is contained in H, we must have H equals n. That's the proof. So it's a pretty strange thing to, the argument is non-trivial, but anyway, it's a simple argument. It's easy to follow. Okay. Next, we have another popular lemma. It's also very useful in various problems. So fix a group and a subgroup H of it. Suppose it has finite index. So we have a group and a finite index subgroup of it. We want to show that if you consider the conjugates of that subgroup and take the union, then this entire thing is going to be the entire group only if the subgroup that we started with was already the entire group. So no proper subgroup, if you form the conjugates of it, you are going to get the entire group back. Even though the cardinalities of all of, the cardinality of each conjugate is the cardinality of H. And if suppose H had big size, let's say H had index 2 in G, any proper subgroup has to have index at least 2. So suppose H had index 2 and it had a lot of conjugates in G, then it would mean that a lot of these conjugates overlap a lot. All right, anyway, so this is also some peculiar statement, but let's see how to. The point I want to get across is the proof technique rather than the statement itself. So first, let us prove this for finite group. So first assume that G is a finite group, and then we will see how to upgrade it to infinite groups. Right? So we want to do it for finite groups, but then, yeah, I need a lemma for it. All right, so first let's prove the lemma. Maybe I will first prove the lemma. So we'll come back to our theorem, but first let's prove this lemma. So suppose G is a finite group acting transitively on some set X. And if the size of the set is at least 2, then there is some group element which fixes nothing. So fix G is nothing but those elements in the set X which do not get disturbed when you act on them by G. So the lemma says that if you have a finite group acting transitively on a set X, then some group element doesn't fix anything. And this was given as an exercise earlier, but since I need it, I am going to prove it. So we will use the Cauchy-Frobenius theorem. Cauchy-Frobenius theorem says that this quantity this is the number of orbits, but since this is a transitive action, there is only one orbit. So this is immediately by Cauchy-Frobenius theorem. And now we will write this sum in, break this sum into two parts. So one is fix of identity, and the other part is just G different from identity. This is equal to 1. And what is the fix of identity? Fix of identity is all of, it fixes everything. So this is equal to 1. Now if this were greater than equal to 1 for all G away from identity, we would have the LHS above is at least this much. Why is that? This is same as that quantity, while if this inequality holds for each element away from identity, then this quantity would be at least this much, and that's all that we did. Right? Which is at least, just shuffling things around, at least that much. But since cardinality of X is at least 2, this is at least this much, which is greater than 1. And that would be a contradiction to this equality. So therefore, there must be some G in this part such that the cardinality of the fix of that is 0, which is same as saying that fix of that is empty. That proves the lemma. It's a very nice proof. There are other proofs, but anyway. So now, having proved this lemma, we come back to our strange, peculiar lemma, which says that if we have a group G, H is a finite index subgroup, then the union of the conjugates of the subgroup is the entire group, only if and only if, the subgroup is the entire group. So first we will prove it for a finite group. Suppose G is finite, and consider the Coset action. So this is a transitive action, as we pointed out, is transitive. By the previous lemma, so assume H has suppose H is a proper subgroup. So assume H is a proper subgroup, that is index is at least 2. That is to say that the size of this guy is at least 2. Okay, so by previous lemma, since the cardinality of this is at least 2, there is some G in the group such that fix G is empty. which implies gx is not equal to, g dot xh is not equal to xh for any x in the group, which implies x inverse g, or okay, let me not skip a step. So this means gxh is not equal to for any x in the group G, which means that x inverse gx is not in H, no matter what x you pick, which is to say that G is not in no matter what x you pick. And hence, G is not in the union of these conjugates. And that proves that this guy has to be a proper subset of the entire group. So if we start with the assumption that H is a proper subgroup, then this guy is a proper subset. And of course, if H is not a proper subgroup, if H is the entire group, then this is clearly going to be equal to G. So that is the trivial direction. The non-trivial direction is if you assume proper containment of the subgroup H, ensure that the proper containment of this holds, which we did. So this is the case for finite groups, but how do we do the same thing for infinite groups? So if G is an infinite proof for infinite, proof for the general case, let me write it that way. So we have G is possibly infinite. Let K be the kernel of the action. Kernel of which action? So again, we are using the Coset action. And K is the kernel of the action. We know that maybe I should write N. Let me write N because I have been writing N previously. So N is the kernel of the action. We know exactly what it is, but we don't need to know it. That's what it is. And we know that since H is finite index, so this is also finite index. This is what we recalled earlier. And now the action of G on this naturally gives us an action of G mod K on G mod N on G mod H. And what is the action? The action is just this. Gn dot xh is equal to gxh. So notice in the recall we did the same thing. If we have a group G acting on a set X and K and N is the kernel of the action, then there's a natural action of G mod N on X. So that's all that we are doing here. And now the point is that since N has finite index in G, this is a finite group. And we can apply the same reasoning as before. So assume H is a proper subgroup, then this has cardinality at least 2, and as previously, there would exist an element in our group such that its fix is empty. But fix of that is same as fix of G. So when I write fix G, I'm referring to this action, and when I write fix of that, I'm referring to that action. But there's a clear connection between the two actions, and the emptiness of fix of that implies the emptiness of fix of this, and the rest of the proof goes just as previously. So that's a very nice trick, actually. You can pass to a simpler action of an action of a finite group given the action of this infinite group, and that's as we saw is very useful. So yeah, with this I want to end the lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.